Hi, this is an introduction to logic. I'm Mark Thorsby, and this course overviews the basics of categorical, propositional, and predicate logic. Today we're taking a look at categorical logic. In particular, we're looking at the logical operations of conversion, obversion, and contraposition. Okay, welcome back, everyone. So today we're going to be taking a look at our logical operators. Quickly, let me do a sort of quick review here, just to remind you what we've looked at before. What we discovered last time is that in categorical logic, there are four standard types of propositions. There's the A proposition, which is basically all S or P, right? There's the E proposition, which is that no S or P. There's the I proposition, some S or P. And then finally, there's the O proposition, which is that some S are not P. Okay, now by this point, you should be fairly familiar with this. Last time we talked about as well the square of opposition, right, which essentially looks like this. At least we looked at the modern square of opposition, in which the I, the E, the A, and the O, right, these are contradictions of each other. Okay. Now, one of the things I want to remind you that's going to be important here to remember is what each of these things are. Remember that this thing right here is known as the quantifier. And it's as a quantifier, it tells you how many, right? How many of the class we're actually talking about. This, of course, is the subject and the predicate. I won't write that since this is P. And of course, but this last thing here, this R, this is known again as the copula. Okay, and that's going to be important today, especially as I diagram these and go through them. Now, because we're going to see here that what the logical operators do is they switch around and mix these, either they mix around the subjects and the predicates and so on and so forth, so as to come up with statements that have logical equivalence. So let me sort of mention what is logical equivalence. I'm sorry, my handwriting is not that good. Logical equivalence. Logical equivalence means that if you have two statements, and I'll symbolize that by S1 and S2, that if S1 is true, then S2 will be true. Conversely, if S1 is false, S2 will be false. So logical equivalence means that they're the same. And we actually don't use the equal symbol, we actually use a double colon here to symbolize logical equivalence. So if S1 is a true statement or a true proposition, then S2 will be a true proposition if they have logical equivalence. So that just means they're equal in terms of their truth value. Okay, so maybe we can write that. A statement that has logical equivalence is a statement that has equal two statements who have equal truth values necessarily. Oops. Equal truth values. Okay, and that's going to be an important feature because we're going to see that when we do logical operators, essentially what we're going to do is we're going to do something to this statement to come up with a second statement that's going to have logical equivalence in most cases. Okay, and it's interesting here because logical equivalence in many ways has to do with distribution. Let me give you an example here. Let's take a E statement. Let's give you an example here. I'll put EX here for the example. What if I said that no Democrats are Republicans? Okay, no Democrats are Republicans. How do we symbolize this statement? Well, let's do a quick Venn diagram, right? We'll put D here for Democrats and R for Republicans. If we're to symbolize an E statement, it looks like this. You fill in this the little football shape here in the middle, which mean, and remember, when you fill, that means there's nothing there, which means that these two things are totally separate. Now remind ourselves, how does the distribution on an E statement work? Remember, we said that a term is distributed if in the proposition the entire class you learn something about the entire class. And in an E statement, since there's a separation of both classes, both terms are distributed. Both terms get distributed. And one of the interesting properties here is that since both terms are distributed, we can switch around Republicans and Democrats, right? I can write no Republicans are Democrats, and that actually means the same thing because what would the um, the Venn diagram look like for this statement? Well, it would look like this, right? If we had D and R, we'll just keep it the same here, right? If no Republicans are Democrats, the Venn diagram is identical, okay? And so since the Venn diagram is identical, what we see here is that no Democrats are Republicans and no Republicans are Democrats. Both of these statements are logically equivalent, right? So if we called this, let me change the color. If we called this statement 1 and we called this statement 2, what we see here is that statement 1 is logically equivalent to statement 2. Okay? So this is just to give you an example here. One of the things to see here is that each of these operations actually that we're going to go over today actually involves distribution. Distribution is really interesting because it's actually pivotal to the whole function of these things. Okay, so let me let me just erase this, make it a little longer for myself. Um, okay, so that's going to be pretty important here. So let's go over these logical operators, and there are actually different types of logical operators. But in categorical logic, at least for this section, we were just going to be talking about three logical operations. Three logical operations. Now, to say that it's a logical operation or what is an operation, an operation here just means you can think of it almost as a medical operation. It just means we're going to do something. We're going to do something to a statement in order to derive a second statement. So that's all we mean by a logical operation. And to say that we have three logical operations means that we're going to have sort of three ways of operating on a specific sort of statement. Okay. Let's talk about the first logical operation. Uh, I guess number 1 here. The first logical operation we're going to look at is what's known as conversion. And conversion is actually quite simple. Conversion consists of switching the predicate and the subject. Um, so to convert a statement is to switch the subject and I don't know why this computer does this. Switch the subject and the predicate terms. Okay? So if I was going to draw a diagram of it, right? Remember, we always have a quantifier. For some reason, this computer cannot recognize that. Right? You have your quantifier, your subject, your copula, and finally you have your predicate. That's essentially what every categorical proposition looks like. And so to convert a statement, all we do is just switch these two guys around. Okay? And in fact, if you'll notice in our earlier thing with an E statement, this is what you do. Now, here's the thing. When you convert a statement, it only works for E and I statements alone. Okay? So remember, so that means you can go from no S or P is logically equivalent to no P or S. Okay? And conversely, remind yourselves what's an I statement. An I statement is that some S or P, this is logically equivalent to some P RS. Okay? But here's the trick, is the logical equivalency only works for these two. And I'm going to write it in red here. What about the A and the O statements? These are not logically equivalent. There's no logical equivalence At least there's no necessary logical equivalence. Hmm. There's no logical equivalence here for the A and the O statements. And it has to do with distribution, right? And we could draw Venn diagrams. I'm not going to do that because if you look in your textbook, he does that. And I'll show you that here in just a second for those of you that don't have the text on hand. But why does it matter here? It goes to distribution. Remember, in an E statement, both terms are distributed. In an I statement, neither term is distributed. So as a result, if you switch them, it doesn't affect the truth value. So these statements are the same. So no Republicans or Democrats, no Democrats or Republicans. That means the same thing. Some, let's say some dogs are nice, and some nice things are dogs, right? Those are logically equivalent statements, but it does not work for the A and the O statements. And if you convert an A and an O statement, this commits a fallacy, and the fallacy that we're going to call it here, that your book calls it, is it's called an illicit conversion. An illicit conversion. So that's a no-no. You don't want to commit an illicit conversion. And you're going to see here that one of the exercises you have to do in the text here is if you discover an illicit conversion, you have to cite it. Okay. So that's the first logical operation. Let's take a look at the second logical operation here, and that's called obversion. Obversion. An obversion has two steps, okay? The first step for an obversion is to change the quality. Change the quality. I wish I knew why this thing doesn't work. Obversion. First, you have to change the quality, and second, you have to replace the predicate term with its class complement, okay? So let me write this down. Replace the predicate term with the class complement. Now, at this point in the course, we haven't actually talked about what a class complement is, and so I'm going to have to sort of give you the background there. Okay, well, what exactly is a class complement? So let's sort of do this right here. What is a class complement? Well, let's remind ourselves what is a class, and we'll use a Venn diagram to symbolize it. Let's say we're talking about Republicans, okay? And in this circle here, it's everything in this circle, every Republican would exist within the circle or something like that, okay? So what is the class complement? Well, this is the class. What complements it is what's around it, right? So all of this, let's sort of highlight it. All of this space right here, this is what complements the class, right? This is what's known as the class complement. But how do we define that exactly? So if R is Republican, what's the class complement? Well, the class complement would be non-Republicans or non-R, okay? Because anything around here is not a Republican. So we just say non-Republican, right? And that includes a lot of things. In fact, it includes everything in the universe that's not a Republican. So the class complement is really simple. It's basically whatever it is with the non in front of it. So it's the non-Republicans. Okay, so the class complement is that. That's how you understand the class complement. So let's give an example here. Um, let's take um, let's take an A statement, which looks like this. Let's say that all dogs are animals. Okay, so how does this work? Remember, let's go back here. First, you have to change the quality. Now remember, this right here is the quantifier. What is the quality? The quality is either going to be affirmative or negative. So that's the thing to remember there. I'll just put, it's either affirmative or it's negative. Okay, so you're not changing how many, you're changing what you're trying to say. So if you're changing the quality of an A statement, all dogs are animals, you're going to change it to no dogs are And remember, but you have to, so you have to change this because this is where the quality is contained. But you have to change animals here because this is the predicate term. So you'd say no dogs are non-animals. Now that's sort of an odd way of talking because we don't usually talk about non-animals. But strictly speaking, this is true, right? Because that means that no dogs are non-animals. Well, that makes sense, right? When you think about it like that. Okay. Now here's the thing: is that aversion works for all statements. Okay. So this works for the A, the E, the I, and the O statement. Okay, so it works for all the statements. So that means that there's no fallacy that we would call there's no illicit aversion because it can work for all of them. Now we did let's do a negative particular because this is a universal affirmative statement. Let's do another example here. What if I said that some cats are not brown? Some cats are not brown animals. Let's just say that. That's our statement. Okay, some cats are not brown animals. So how would I avert this statement? Now, that was an A statement. This is an O statement. So how would I do this? Okay, well remember, first I have to change the quality, not the quantity, right? Notice that before I change in this statement up here, I had changed the quantifier in order to change the quality. But here I'm not going to do that. Remember, this goes back, and if you need a reminder, refresher, take a look at one of our earlier videos where we actually discussed um, why there's no qualifier, but there is a quality to each proposition. So remember, the quality is either affirmative or negative. So that means we got to get rid of this not, right? So we don't want to change how many, so we leave some. So that means we want to get rid of this thing, okay? And the predicate term is this, brown animals. Okay, so if we're gonna avert this statement, it's gonna look like this. Change it. Some cats are non-brown animals. And you can see here, it almost seems like we just moved the negation into the term itself. And that's actually exactly what we've done. Is we've taken the negative out of the statement and really sort of negated the term by using the class complement. Some cats are non-brown animals, and this statement is logically equivalent with this statement. And if we did Venn diagrams here, and I'll show you this in a minute, we would see that the Venn diagrams are identical. Okay, so that's the second operation. That's aversion. Okay, that's aversion. So let's move now here to the third logical operator that we're talking about today. And the third logical operator is what's known as contraposition. Or I don't know, I think I was using numbers, sorry. 3. Contraposition. Contraposition. And there's 2 steps to doing a contraposition. Right? The first thing to do is to switch the subject and the predicate. So first thing you do is something, you do sort of a conversion. So you're going to switch the subject and the predicate. And I'm just going to write it like that. So first thing you do is you switch the subject and the predicate. And the second thing you do is you replace both subject and predicate with their class or term complement. Okay? Replace both subject and predicate with their respective with their respective class complements. Okay? Okay, now here's the thing. This works, right? Notice we said that the conversion works with the E and the I. and we say that aversion works with all of them, the A, the E, the I, and the O. The aversion only works with the A and the O statements. It doesn't work with the E and the I. Okay? The E and the I, if you contrapose an E statement or an I statement, you will not end up with the statement that is logically equivalent, right? So that means that this will create a fallacy, which we're going to call the, no surprise here, the illicit contraposition. Microsoft Word is giving me trouble today. Sorry about this, guys. Okay, the illicit contraposition. Okay, so let's do an example here of a contraposition. Remember, you switch the subject predicate and you replace each of those with their term or class complements. So here's our example. Okay, let's take a O statement. Well, let's take it. Yeah, let's just take an A statement here, which is something like all citizens are voters. Okay, all citizens are voters. Okay, so how do we do a contraposition here? Well, the first thing we got to do is we got to switch the subject and the predicate terms, and then we're going to replace them with the term complements. So let's go like this, and I'll just write here, replace with complement. Okay, so it's going to look like this, right? It's going to be all non-voters are non-citizens. I'm sorry, guys. This is really annoying me. All voters are non-citizens. Okay? Now, this is logically equivalent. And actually, if you think about it, if I say all citizens are voters, and then I said, well, all the non-voters are non-citizens, that actually makes sense. And if we did a Venn diagram, it would work. Okay, so real quick, let me show you here what the Venn diagrams actually do look like for each of these logical operations. And here we're just taking a look here at the textbook. Okay. So you can see here, if we look at the conversion of an A statement, you can see here, right, that these Venn diagrams don't look the same. Thus, they're not logically equivalent. See how these Venn diagrams do look the same? They're logically equivalent. Same, they look the same, logically equivalent. The X's on two different sides, they're not logically equivalent, okay? So there you can see the conversion. If I did a Venn diagram for this, notice that each of the Venn diagrams looks identical for each of the statements. Thus, for aversion, logical equivalence works for any of the statements, okay? And then let's scan down here to contraposition. Take a look at the Venn diagrams. Notice for the A statement, they look the same, so that means you can do a contraposition. But take a look here. If no A or B, if I do a contraposition there to no non-B or non-A, well, if I was trying to do a Venn diagram, I'd actually have to fill out all of this stuff. Those don't look the same, so they cannot be logically equivalent. Right? Same thing. These look different. They're not this logically equivalent. Down here, they do look the same, so they are logically equivalent, which means that if this statement is true, this statement will also be true. If this statement is true, because they're not logically equivalent, the logical value of this, the truth value of a contraposed I statement is unknown. It's unknown. The logical value is unknown. So that means it's a fallacy, illicit contraposition. Okay? And that, in essence, is what the three logical operators we're looking at are. Contraposition, aversion, and of course conversion. Now, one of the other thing I should mention here is that one of the things that, what's this? One of the things that your book is going to do is it's going to be, you can use logical operations to test immediate inferences. What is an immediate inference? An immediate inference is basically it's not really an argument, but sort of like an argument. It's if you have a premise and then what can you conclude immediately from that? So there's only one premise and one conclusion, right? So for instance, using these logical operations, right? Um, well, actually, here, let me go back here. Let's do an example here. Let's say I want to avert an I statement, right? Now remember, you can avert I statements because aversion works for all of them. So let's say if I said that some people are mean individuals or something like that. I'll put I here for mean individuals. Some people are mean individuals. If I wanted to avert that, how would I do it? Now remember, aversion was where I had to change the quality. So I have to put this into a negative, and then I have to replace the predicate term. So it would be that it would change to some people are not non-mean individuals. Now you can notice here that I obviously don't talk like that, but this is what an aversion would look like here. Okay, so this you can see here, since these are logically equivalents, if you made an immediate inference here, if someone actually said in an ordinary argument, which would be sort of odd, but imagine if someone said to you, some people are mean individuals, therefore some people are not non-mean individuals, right? If someone said that to you, you could test the immediate inference, and you could realize that all they've done is avert the statement, and since the truth value of this one, after it's averted, is logically equivalent, that would be a valid immediate inference. Whereas, for instance, if I tried to convert an O statement, right? If I had an O statement and then I converted it to something, and I tested the immediate inference, I would say that no, that's not logically equivalent. And in fact, that actually commits the illicit conversion fallacy. Okay, one of the things you'll find if you have the textbook that is quite helpful is there's this sort of diagram here, right? Where, right, here's the the I statement. Here's what their converse look like, and these have the same truth value. They're logically equivalent, whereas these have undetermined truth values and therefore commit the fallacy of the illicit conversion. And this aversion, they're all the same, but here's what they would look like. And then for contraposition, these have the A and the O have the same truth value, but these are undetermined, the E and the I. Okay, and so what your homework is going to ask you to do, if you're doing the homework here, is they're going to give you statements, and then they're going to say, do a conversion. What does the new statement look like? What's its truth value? Okay, and as you go through this, you'll even get some that say, here's one statement, here's another. What operation was done, and what's the new truth value? Okay. And so it's actually pretty fun to do, and it's not difficult. But we're going to see later on that these three operations actually are very helpful to do when you're actually assessing arguments. But right now, all I want you to get is to get how this works. Now, you can see here that what they're going to have you do in the homework is they're actually going to give you statements, and then they're going to ask you here, perform aversion, conversion, contraposition as indicated. So they want you to convert the statement. All of these statements. Let's take this one. Right, some murals by Diego Rivera are works that celebrate the revolutionary spirit. Remember, a conversion is you just switch the subject and the predicate. So if you converted this, it would be some works that celebrate the revolutionary spirit are murals by Diego Rivera, and then you got to figure out whether or not that statement commits a fallacy or not. Okay, so that's what the homework is, and that's essentially how you do the logical operations of conversion, aversion, and contraposition. Okay, well, thank you guys for watching the video. I hope this was helpful. In our next video, we're going to be looking at the traditional square of opposition, and you're going to see that things get a little more complicated, but actually much more interesting. And then we're going to also go back to the importance of talking about the existential fallacy. Okay, thank you very much for watching. I'll see you guys online.